Okay, welcome to today's class, and please pay close attention because in today's class, I will be talking about a lot of important concepts. Some of you may already know, or some of you may not know, on how to implement functions, sub-functions, and how to interpolate between different data structures and how to map different data structures so the MATLAB code can run in a Simulink environment. But before that, let me wrap what is left. In the last class, we talked about two things. In last class, we talked about the gravitational forces, aerodynamic forces, and then we are looking at now the prop thrust and torque. So prop thrust is very important because that actually pushes the aircraft forward. And here is the simple equation for the prop thrust and torque. Please note prop torque is sort of unwanted phenomenon that comes into the picture because of the Newton's third law. Every action has equal and opposite reaction. However, when the prop generates a thrust, the reaction thrust acts on the aircraft that propels the aircraft forward. And this equation needs to be programmed in our simulation so that we can run the simulation with realistic prop implementation. So if you look at the coefficients for thrust and torque along with the advance ratio, which is a dimensionless ratio, you would realize that it's sort of a quadratic equation. And you can implement this equation in your program so that we can accurately model the coefficient of thrust Ct and coefficient of torque Cq as a function of advance ratio. And this advance ratio is dependent on two parameters. Advance ratio is dependent on the airspeed as well as the prop velocity. So if you look at a simple implementation, you are not using an internal combustion engine, but you are actually attaching that prop to a DC motor. It's a very simple RC type of airplane configuration. So this is the governing equation for the DC motor. Torque generated by the DC motor is equal to KQ in the parentheses 1 divided by R, V in, which is the voltage supplied, minus the back EMF. Back EMF depends upon the RPM of the rotor minus the I naught, which is the current at the no load. This is something we discussed in robotics 1 when we looked at different types of actuators. So this is the governing equation for a simple DC motor, and we would use that equation in our simulation. Now, for the time being, I'm not going to discuss this second order equation, which talks about the stability and other stuff. But if you want to think about this equation, as you can see, capital omega can be written as a quadratic equation. You can find the roots and then you can find out the appropriate advance ratio. And these coefficients essentially A, B, and C. So what this equation is doing, it is giving us the values of A, B, and C with regards to the advance ratio, operating advance ratio, which is J op. And this is very useful when we actually look at the simulation. So in essentially what we did here is we combined the motor torque equation and the equation for thrust and torque and came up with an equation that can be used. Next part is the Python implementation that I'm not going to look at in detail. But what I want to emphasize on, so if you were to implement your simulation in Python, Okay, can you hear me? Okay, for some reason Zoom cut me out. So, all right. So now what we are trying to do here is we are trying to implement the wind model, and the wind model is comprising of actually 6 quantities. The first 3 quantities are the steady state quantities of the wind, and the last 3 quantities are the instantaneous variations in the wind. So what I want to talk about is wind can help you or can hurt you. What that means is if you have a good tailwind, your effective speed is increased and the fuel consumption is decreased. If you have a headwind, which is actually resisting your motion, then you will have to spend more fuel to overcome that wind resistance. So the equation that I want you to look at, and look at this equation very, very carefully, is VW comprises of 2 components. And these 2 components are, one is the steady state component. This is the steady state. And this is the changing component. And the wind changes depending upon altitude, depending upon the location, depending upon the airspeed. There are a lot of factors that come into wind model. But the good news is researchers have developed turbulence models, and there are standard wind gust models that we can use for our analysis. And just to give you an idea, these gust models can go from a very simple model to a very sophisticated wind model that takes into account the local wind conditions. So if you have the ground weather stations, they can actually access that information, the GPS coordinates, and then give you quite accurate prediction of the wind at particular time of the day, at the particular time of the year, depending upon the data that is sent by the weather station across the globe. So one thing I want to tell you is there are 2 things that you need to be very careful about. Please note that these 2 components can be separated as VIWS and VBWG. This is the steady state component. And this is expressed in inertial frame. And this is the gust component that is expressed in body frame. So now what we need to do is we need to have a component of airspeed or wind speed in the inertial frame that somehow we need to map into the body frame, and we have to incorporate the gust component, and that is actually given in body frame, so we have to add to it. Now MATLAB fortunately has these models implemented in the Simulink, but I'll tell you conventionally how it is done. Conventionally, what you have is you have a transfer function for the wind gust in the U direction, wind gust in the V direction, and wind gust in the W direction. So this is a transfer function model. And if you recollect in robotics 1, we talked about what a transfer function is. Transfer function is the ratio of output divided by input in the Laplace domain. And what we do is we feed a white noise input to this transfer function, and then this transfer function gives us an output which is nothing but the wind gust in U direction, V direction, and W direction. Once again, this is in the body frame. So body frame, and body frame. So you have a transfer function that you input white noise, and that gives you the gust component of wind in U direction, V direction, and W direction. Also, you have a steady state component. So this is the gust component. Gust in U, gust in V, and gust in W. And you have the steady state component that is given in inertial frame. And that needs to be fed to your rotation transformation so that you can map all these components into body frame. And at the end, when you have the steady state component of wind in the body frame and the gust component of wind in the body frame, you can combine those to find UW total, VW total, and WW total. Now, the way you implement these transfer functions is these are the standard transfer function for something called as Dryden Gust model. This model is developed with experiment and theoretical analysis. And the idea is for different altitudes, you have different values of these constants. So for different altitudes, you have the different values of these constant. You have different values of distribution, sigma, and you use that and then feed the white noise through this, and you're gonna get a variation of gust that would replicate the low altitude light turbulence, low altitude moderate turbulence, medium altitude light turbulence, medium altitude moderate turbulence values of wind gust. Now, I just want to tell you, if you were to start with these transfer function models, it's possible to start with these transfer function models and implement these using MATLAB. Here is the MATLAB implementation of Dryden Gust model. Then, or if you create a class transfer function and then implement all that, it is possible to perform this implementation. But at the end, what we want is, let's keep our eyes on the prize, is we want the wind vector. This is the thing that we are looking at. So no matter whether you use transfer function approach or whether you use maybe the MATLAB Simulink approach, the idea is finally we want the wind that comprising of the steady state component and the transient component in the body frame. So the idea is once we have the wind vector, we can find out the airspeed. So this can be used to find airspeed, as airspeed is the velocity u v w minus the wind speed. So you have a forward velocity u minus, if you subtract the wind velocity, you are gonna get the velocity ur. If you have a velocity v, subtract vw, you are gonna get vr. Same thing, if you have w velocity minus wind velocity in w direction, you're going to get vw. And this all together gives you the component. These are the components of airspeed. These components give you angle of attack. This is the actual angle of attack. And this gives you actual side slip. Now, this is very important because you might have, from the control, you might have set angle of attack to particular value, but the actual angle of attack is function of the wind velocity. So what you need to do is you need to VR. Yes, this is VR. So VR. So what actually you need to do is the actual angle of attack can be determined based on the wind speed and the actual the aircraft velocity u, v, and w. U, v, and w are the velocities in x, y, and z direction at the aircraft in the body reference frame. Subtract the wind velocity in the body reference frame, and you get the airspeed in the body. Then you can find out the angle of attack, and then you can find out the actual side slip. These equations are super important. So please pay attention to what we are going to do. Now, let's go back and see what are we trying to do in simulation? And I'm going to go back to the very basic where it all started. So we are trying to simulate these equations used inside the MATLAB. Now, if you look at the set of equations that we simulated earlier, our forces were 0, our torques were 0, and we simulated the equations. Now, what we need to do is we need to add the values of forces and we need to add the values of torque. Forces will comprise of gravity, aerodynamic forces, and prop thrust, and the torque will include the values of torque that we compute from aerodynamic moments and then the prop torque. So I just need to talk about the interdependencies, and this is something very useful when we do this project. So let's start with where we were. So we have a function, this is in MATLAB, which is something called as derivatives 1. .m. This MATLAB function has the differential equation implemented. This is project 3. Yeah, this is project 3. Sorry, this is a typo. This is project 3. So this MATLAB function has a derivative 1.m implemented. This derivative 1.m needs to use force moment equation, force and moments. There is a function for force and moments. This function needs to be used by derivative 1.m. However, I want you to understand the interdependency. To find force and moment, you need the instantaneous values of states. Then you need the values of the input, which is the control surface. And this force moment needs additional input from a function which is called prop force torque. So now what we have is, we have all these three functions which are interdependent. So we have to make sure that when we implement this either in MATLAB or in Simulink, all these interdependencies are preserved. The implementation is simple in MATLAB, and the reason for that is because the data structures don't need any modification. So in the last class, I gave you a partially working code for MATLAB, but there was a mistake and I left that deliberately. So I want to see if how many of you caught that. So what I'm going to do first is I'm going to go back to the MATLAB scripts that I uploaded. And then what I would suggest you all to do is make a copy of that folder in your desktop. And we'll start with that copy and then start modifying it step by step. And at the end, you should have a working template for the code in Simulink. So let me be very clear. We will start with the MATLAB codes in last class, which was chapter 3 discussion. And then what we will do is we will step by step integrate these MATLAB codes in the Simulink environment. And you will have to work on this Simulink environment to come up with an integrated solution to project 3, which is add simulation, wind simulation, add forces, and then verify your simulation. Yes, I'm talking about delta R values when I talk about inputs. Everyone understood the process, what we are going to do? Any questions about the process? So we are going to start with something that we worked on in last class, and step by step, modify so that we can actually implement the Simulink code. But once again, I am not going to give you a complete solution. So this solution will be incomplete. And it's your assignment to take these skeleton scripts, skeleton code, and then implement what is needed for project 3. Any questions so far? If not, I am gonna shift to MATLAB. Okay, step 1. Everyone should be looking at project 3 class discussion, the folder that I shared in last class. And what I want you to do is, I want you to make a copy of this folder. So please make a copy of project 3 class discussion. And once you make project 3 class discussion copy, you can actually paste it into the desktop, and that gives you a project 3 class discussion copy. Now I want to go to MATLAB. I want you to go to MATLAB. Now in MATLAB, what I want you to do is just go to desktop and add project 3 class discussions copy in, so let me go show it to you again. Go to desktop, and then you will see project 3 class discussion copy, and then add that to path and folders. So once you have that, you can open project 3 class discussions, and then it will give you this all the files that you used in last class. So I want you to make another copy of project 3 class discussion so you can see. No, it's not Mavsim Ghazi, it's just the project 3 class discussion folder that we used in last class. We are not doing anything to Mavsim yet. It is just we use the project 3 class discussion MATLAB files. And then first I want you to open derivatives 1. And I want you to go through derivatives 1 and look at the forces. So this is where we invoke this function, forces underscore moment 3 x delta I and wind. Now, I don't know if anyone caught the mistake or not. This was a deliberate mistake. Please note, and this is very important, that the forces are used here, fx, fy, fz. Moments are used here, m, n, and l. So L, m, and n. These moments are used here, but the function forces moment sp3 is called after the forces and the moments are used. So what it's going to do is it's going to use the default values for forces and moments that we obtain from F states, and those values are 0. In other words, if you run the script as is, and let me try to make the font a little bit bigger. . So if you use the forces and moments as is, then when it computes the values here, it's going to use 0. Now, what I want you to do is, I want you to take this equation, so out one from line 63 to line 70. Actually, you can take all this. So highlight from 57 to 70, cut and paste it over here. So what this means is every time when you run the code, the forces and moments will be calculated at that instant. So what I want you to do is, I want you to copy the out forces moments and then paste it here. And if you need this new function that we just modified, I can send that function via the chat window. So I can send. Yeah, Ghazi, what is your question? Okay. So I'm gonna give this function, copy, paste, copy, paste, and the last part, copy, paste. So this should be inside your derivatives 1. Now what I want you to do is, I want you for a minute to save this function, and then I want you to run simulation run. Out one prime, you have to comment. You can comment. Okay. So, all right. What I want you to do is, so here is the issue that was in the earlier code. In the earlier code, the function forces moment sp3 was called at the end. And when we call that function at the end, the values of forces that we obtained, those were not used in the simulation. So what I'm trying to see here is copy the code which is starting from x is equal to something all the way to out one prime. Yeah, out one prime is deliberately commented. And then paste that code before position kinematics. And now if you are still having questions, then what you should do is, you should look at the chat window. In chat window, I have copied and pasted this entire file. Just use that syntax and run in your derivative 1.m file. Okay. Okay, I think I lost some. Does anyone have any question? Now what I want you to do is, I want you to open simulation run. And in simulation run _m, just run the file just to make sure that your simulation is working. And you should see your UAV emerging from a point. And one thing that I want you to notice, that this simulation is different than the simulation that we obtain, or the result that we obtain in last class. Can you hear me? Okay, fantastic. So what I want to tell you is simulation underscore run dot m and run the code. Simulation underscore run is in the project 3 class discussions copy. And it is different because now every time the simulation runs, the instantaneous values of forces and movements are calculated and applied on the airframe. That to answer Zubir's question. So I just want to make sure that, and now then you will see something interesting happening. You may see that simulation may freeze up, and the reason it will freeze up because it may reach to a numerical singularity. We will address that a little bit later. So if you want to get out of the simulation, I want you to press Control C, and then you will get out of the simulation. Now, before I go any further, everyone got this preliminary simulation working with the instantaneous values of forces? And can you notice that this simulation or this result is significantly different than the result that we obtained in last class? Okay, now I want to migrate to Simulink. So everyone, please pay attention. I'm gonna explain the steps 2 times, and then I will give you some time to implement it yourself. So please pay attention. Now, here is what I'm going to do. I'm going to take all these MATLAB functions and embed in a Simulink environment. And it is not easy, or it is not trivial, because the data structures that are available in MATLAB may or may not be available in Simulink. The native functions that are available in MATLAB may or may not be available in Simulink. So there is some amount of trial and error needed. And I'm gonna do this with you. So what I want you to do at this point is open Simulink. So click Simulink, and the Simulink would open. Then I want you to click on blank model, and a blank model will be created. Now at this point, I would like you to see I have my MATLAB window on the left hand side, and I have my Simulink window on the right hand side. MATLAB window on the left hand side and the Simulink window on the right hand side. I'm going to start with the easiest system or easiest code, and that code is, I want you to open prop thrust torque m. So look here, prop underscore thrust underscore torque dot m. Once you open this code, I want you to quickly go through this code. What this code does is this code will find out the magnitude of thrust, torque, speed, and current for a given value of airspeed, VA, for a given value of airspeed, and the throttle input. Delta T is the throttle input. So you can set the throttle input to 0, that means there is no thrust. You can set the throttle input to 1, that means the prop is providing the full thrust. Now what I'm going to do is, I'm going to encode this function inside Simulink. So I want to go to the Simulink environment, go to library browser, go to user defined functions. Are you with me? Are you in the user-defined function? Simulink, library browser, user-defined functions. There are a lot of ways user-defined function can be implemented. But what I'm going to do is I'm going to select MATLAB function. I have highlighted MATLAB function, drag and drop in the Simulink environment. Once you drag and drop it, you will have this MATLAB function in the Simulink environment. Everyone got the MATLAB function in the Simulink environment? Double click on this Simulink function. As soon as you double click on the Simulink function in your MATLAB, you will have a MATLAB function. You will have a MATLAB function. What I want you to do is, I want you to go to prop thrust torque file, the file that we just opened, grab this function all the way from here. So copy function from line 29 all the way to line 57. Copy function from line 29 to line 57. Copy and paste it in this new MATLAB function that we just created and delete old function. So now what you should have is, you should have a MATLAB function that represent this Simulink function that actually will take VA and delta T and give you the output thrust, torque, omega, and current. Yes, Ghazi, once you actually open the Simulink file and paste it, this MATLAB function in the Simulink MATLAB function, actually your SLX file will automatically be created. So if you look at this function, one thing I want you to understand, and this is super important, that this is the input to the function. That's why it is in the parentheses. This is the output of the function. That's why it's in the square brackets. And everywhere there is a comma. Please note, this is a comma. This is not a semicolon. I will repeat again. This is a comma, not a semicolon. This is needed. This will be needed in the next part of the discussion. So what I'm going to do is, I'm going to save this. Okay. So, no, I didn't say delete the prop thrust M. What I'm saying is, copy prop thrust underscore torque M from line 29 to line 57 and paste it in here. Don't delete anything at this point. We haven't deleted anything. Then save. Once you save, it will ask you for the save file name. And I want you to notice this. This is not saving a MATLAB function, but it is saving a Simulink file. Once again, not saving MATLAB function, but it's saving a Simulink model. So I'm going to call this Simulink model prop thrust underscore run. Prop thrust underscore run, and maybe 1 in case if you have to go through a lot more iterations. And then save this. And I want you to watch the screen very carefully what happens when I save it. Watch the screen very carefully when I... Yes, the name. Yes, John, name is important. Think about my last name. Instead of red car, it's red car or blue car. That would be different, right? Because this function will be used again and again as part of subfunctions. Now wait a second, not yet. So once you save this, I want you to observe that this MATLAB function all of a sudden change the description and change the inputs and the outputs. And believe it or not, this whole thing got added directly to the path. So can you see prop thrust run 1 SLX is already in the path. Borna, this is to answer your question. So as soon as you create a Simulink file, the way we discussed, it will automatically be added to the path. Yes. Now, what I want you to do is, I want you, whenever you create a complicated Simulink code, it's always a good idea to start with a step-by-step approach. Here, the input is VA delta T. VA is the airspeed, delta T is the throttle input. And thrust, torque, RPM, and current is the output from this block. So what I'm going to do is, I'm going to go to block library, and I just want to make sure that this code, standalone code, works. So what I will do is, I will go to constant, grab constant over here, another constant, grab constant over here, and I'm going to supply this to VA, and I'm going to supply this to delta T. So for an example, what this means is, say, if I have an airspeed of 300, and if I have a throttle input of 1, I want to observe what is the output of this block. So I create a scope, make this scope a little bit bigger, and then attach thrust, torque, then RPM and current to the scope. So I'm going to attach thrust, torque, current, and this guy. So what it's going to do is, when I run this code, it's going to take the input of 300, input of 1, and then it will show me the output of this block. This is super important just to make sure that this block is working, because many a times the MATLAB code on its own will not work if the data structures are not mapped correctly. And say run. And when you run, if everything is good, you will get some output from this block. And please note, this is just a constant output because we are supplying constant airspeed. If you want to see if this block can take varying output, this is very important. If on check if this block can take varying output, you can go to sources, and then you can add maybe a sine wave. So you can go and add a sine wave. So you can go to sources, grab sine wave, and then run again and look at the block and see if you change the sine wave parameters, if the values get changed. So that is how you will make sure that your code is running. Okay, I will address this question in a little bit. Just hold on for a second, because in the next code you will see what happens if the data structures are not consistent. So bear with me for a second. So I just want to make sure that everyone got this simple Simulink code working. Okay, now what I want you to do is save everything and close. Now what I want to do is, I want to create the Simulink file for the next function. So once again, Simulink. I close my scope, Gazi. So, but I will. So now I want you to open another blank canvas. Another blank canvas. Simulink. The next function that I want to code in Simulink is forces moment sp3. So double click on forces moment sp3. Yeah, you can close the last one. That's totally fine. And now everyone should have force moments p3.m in the MATLAB window. Everyone with me so far? So you should have force moments m, and this is a big file. Now, so we are going to make some mistakes, okay? And I want to make these mistakes so that I would like to show you how you can debug errors in Simulink. So everyone, please pay attention. We are going to make some mistakes, but we are going to make mistakes so that we can systematically debug the Simulink code. I'm going to follow the exact same procedure what we did in the last Simulink file. Library browser, user-defined function, grab this MATLAB function and paste it over here. Now what I want to do is, I want to double click on this MATLAB function, and all of a sudden new MATLAB function opens up. This is a new MATLAB function. And what I want to do is delete whatever it is in that function. Delete whatever we have in that function. Go to force moments sp3m, copy from line 15 all the way to line 156. Copy line 15 to line 156, paste it in the MATLAB function that we just created. So your function, the new MATLAB function, should look like this. Now one thing I have to be very clear. This force moment sp3 function has three inputs. X, that are the states, Pn, Pw, Pd, and all those 12 states. Delta are the inputs from the elevator, aileron, and rudder. So that those are the elements, the control surfaces. And wind is nothing but a structure, or it's a 6-element vector that takes the wind loading. Now at this point, we don't have anything defined. I copied everything. So in force moments, the function starts from line 15. It goes all the way up to line 156. I highlighted and pasted that in here. Now what I'm going to do is I'm going to save. And as soon as I save this, it's going to ask me to save another Simulink file. And I'm going to call this force_run. Force_run. Now, as soon as I save, look what happened. All of a sudden, if you look at this MATLAB function, it changed. Now you have X, delta, and wind, and you have an output. Once again, you have X, delta, and wind. Let's look at what these are. X are this 12 element vector. So if you look at this Pn, Pe, Pd, Uv, W. So what I'm going to do is I'm going to apply an input, go to library browser, go to commonly used block, grab constant, place it over here and double click. This is just one constant, but I want to send a vector. So it's a 12 element vector. So I need to send, I'm going to type 12 times, 1 comma 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 1. So 1 2 3 4 5 6 7 8 9 11 10 11 12. So this should be 1 2 3 4 5 6 7 8 9 10 11 12. And please note there is a semicolon after each one. So now this is a 12 by 1 vector, and then connect it over here. Grab another constant, place it over here, and this constant is again 1 comma 1 comma 1 comma 1 and semicolon 1 semicolon 1, because this is the control input. So these are the deltas. So it go over here. Now for the wind, for this iteration, wind is a 6 element vector. Again, grab this constant over here, and I'm gonna say just 0 comma 0 comma 0 0 comma 0 1 2 3 4 5 6. So this is a wind vector. You need bracket. Yeah, you need bracket because it's a vector. You need bracket because it's a vector. You need bracket because it's a vector. Now what I'm going to do is I'm going to try to do the same thing what we did earlier, is grab the scope and paste it over here. So everyone is clear with this Simulink block? The size of the second one is 4 by 1. And it should be, I'll open that for you clear real quick. Bracket 1 semicolon 1 semicolon 1 1. The last one is all zeros because we are assuming no wind. Everyone with me so far? How many zeros? 6. Of course, it won't run. All right, let's try to run it. And I am pretty sure that you will have a long list of errors. Everyone got errors? Right. Now, these errors, and I want you to tell you what this error means. Undefined function or variable force. The first assignment to a local variable determines its class. This is a classic data structure mismatch error. This is a data structure mismatch error. No, Borna, I'll explain that in just a second. You don't have to link the parameters because these parameters are in the same folder in the workspace. So the function will automatically grab the parameters from UAV parameters. You don't need to link the parameters separately. And please note, if you go through these errors, there is no error on the parameters. It's not saying that UAV parameters are unknown. What it is saying is Simulink cannot determine the size or types of the output for the block. And the reason for that is the data structures are not matching. Now, what is not matching? So something clearly is wrong with the force. Now I want you to go back to the MATLAB function. This is super important, so please pay attention. So now, let's go step by step. Clearly, please note, there is a question mark at the out. There is another question mark at the out, which means the Simulink doesn't know what is the output. So here is what I'm going to do. So Everyone pay attention to the MATLAB script. I'm gonna go down 5, 6, 7, 8, 9, 10, all the way 30 and see where this force guy is. Now, please note, line number 61, row value, you may have to change it. Once again, line number 61, row value, you may have to change it. Now, I want you to go down and all of a sudden, can you see that I'm getting errors in force? And when you hover your mouse on the force, it actually, Simulink is smart. It tells you that code generation requires variable force to be fully defined, which means the data structure should be completely known. So here is what I'm going to do. Rather than defining force as an element of a vector, I'm going to define that as a scalar variable. Once again, I repeat, rather than implementing force as an element of a vector, I will define this as a scalar variable. What do I mean by that? So now, can I see there is force underscore 1, there is force underscore 2, there is force underscore 3, force underscore 1, force underscore 2, force underscore 3. Then go down, go down, go down, and see where else this force is appearing. So we corrected force on line 71, 72, and 73. Force appears on line 94 and 95 on the left-hand side of the equation, as well as on the right-hand side of the equation. So this needs to be changed. So make this change in 94 and 95. Same thing in 97. Then go down. You are welcome to run the code at this point, but recognize that you have another error. If you go down to the error, there is an error, same error for the torque. Look at the error for the torque. No, what we did, we converted force, which was defined as an element of a vector, into a scalar quantity because Simulink cannot handle that data structure inside the MATLAB script. That to answer John's question. Now you have an error on torque. So change this error to get rid of this error. Torque 1 on line number 106, torque underscore 2 on line number 114, torque underscore 3 on line number 120. Go down. Then here comes another issue. In line number 132, you have again force defined. So take this out, make it into a scalar quantity, take it out, make it into a scalar quantity, and the last part is I need to change this to force 1, force underscore 2, force underscore 3, torque underscore 1, torque underscore 2, torque underscore 3. However, this will also give me a problem. So what I'm going to do is I'm going to take all this output from here, copy, comment this, and add this over here, the very first function. And I understand that this may be a little bit difficult to follow. So what I'm going to do is I'm going to give you the script, but please understand this script is also given to you in the latest Simulink files. So I'm going to copy this code. First 29 lines, copy, in the chat window. Next, 30 to 60. Copy in chat window. Then 60 to 82, 83. In chat window. 84 to 104, 105. Copy. Chat window. 106 to 128. Copy. Paste in chat window. And 129, 143. Copy and paste it in chat window. And save. Force _2. No, that should be a semicolon. You are absolutely right. Oh, actually, I made a mistake. So everywhere there has to be a comma. So this is not a semicolon, and I want you to understand this. Try this with a semicolon instead of comma. Try this with a semicolon, and MATLAB will give you an error. Try this with a semicolon, and MATLAB will give you an error. This has to be a comma, 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 comma. Everywhere it has to be a comma. Say. Yes, John's observation is correct. But let's see if this thing works. And now I have good faith in this system because all of a sudden I have all these quantities showing up. So what I can do is I can do the same thing that we did earlier. Connect, 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 and connect. So your Simulink should look something like this. And now let's see, if you run this, let's see what happens. You run this, double click, and you got an output, which means the function that we encoded in Simulink seems to be working. Any question here? See, MATLAB is smart. Okay, this rubric question I will address. Yes, rubric will be posted. But first, if you have any questions related to the material that is being discussed, I would like to discuss that first. Now, Jax, we are not there yet. There's still a lot of work that needs to be done. Okay, so next step is, yeah, you can send that to question to MATLAB or MathWorks. So that is to answer Zubir's question. I don't know either. But if you want, I have a student who works in the MATLAB development team. I can give you his email address and you can contact him directly. Okay. Now, one thing I want to tell you here is the wind model is inaccurate. We used all zeros. Now, what I'm going to do is, instead of writing the transfer function, I'm going to go to library browser and watch. Google, in the library browser, search for Dryden, D-R-Y-D-E-N, Dryden, and you click on Dryden. Assuming you have installed all the block sets that we asked you to, including the aerospace block set, you will have the Dryden model inside your block set. This is the wind model. Dryden model is the wind model. Grab this model and paste it over here. And then what we are going to do is, once again, there are 4 different Dryden models for low altitude, high altitude, low turbulence, high turbulence. But just grab the simplest one, the low altitude one, continuous. Grab it from here and then connect it. This is the wind model. Now here, aerospace block set. But what I suggest you do is, you go to a Simulink library browser and Google Dryden. Put Dryden, D-R-Y. So when you install MATLAB, it will ask you if you want to install all the toolboxes. The recommended thing is yes. But for some reason, if you did not install the toolboxes, you will have to go to MATLAB, go to Home, go to Add-ons, click on Add-ons, and then go to Aerospace block set. So just click here, Aerospace block set, and then it will open the aerospace block set, and then double click, and then it will download and install the aerospace block set for you. So we need this aerospace block set. Please note, this block set is available in R2020B. That's why we asked you to upgrade to R2020B. So go to add-ons, go to aerospace, download this block set. Okay. Jade, does that answer your question? And Ghazi, does that answer your question? Okay, cool. Now, once you have your Dryden model, again, the story does not end here. This Dryden model is going to need, this is implemented slightly differently. This Dryden model is going to need an altitude, airspeed, and it's going to need the direction cosine matrix to map the static velocity or the steady state velocity onto the body coordinate. Now I'm going to give some input to this. Constant. This is the height or the altitude. I'm going to say the altitude is maybe 300. I'm going to say my airspeed is maybe 20. I don't know if there is alternate to Dryden. 20. You can check. I don't know. And then DCM is a direction cosine matrix, which is a 3 by 3 matrix. Now here is something important. The way we are going to implement in our simulation, it's gonna be identity matrix. So 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. So this is an identity matrix. So our the direction cosine matrix will be an identity matrix. So Zubir, I think what you may have to do is you may have to uninstall 2019 and then install 2020B. So that is something I would try. Now I want you to understand that if you double click on Dryden, it will actually ask you for all this information, including the noise seed, which is, if you look at what these are the gust parameters, the UG, VG, WG, and PG, the white noise, and it will ask you for the UAV wingspan. You can keep it at 20. It will also ask you for probability of high altitude intensity. It will also ask you for scale length, wind direction, and wind speed at 6 meters for low altitude intensity. You can actually implement this with different mil specs, but I'm going to use mil 8785, and it will also ask you if you want the velocity in feet or if you want velocity in meters per second. I will stick to meters per second. Now, once you click OK, now this will give you input to the wind, but there is something else I want to talk about. If you just want to see how the wind velocities are going to look like, what you can do is you can have another scope wherein what you can do is you can connect this scope to wind velocities and wind angular velocities. So your Simulink file at the end would look something like this. And I'm going to wait here for a second just to make sure that everyone has the same code. And then you should run. And when you run, okay, it gives an error. So let's see if that error is because of, oh, yeah, because this is requiring wind in 6 element. So what you need to do is constant, go here, change this constant to 1, semicolon 1, comma 1, okay, and then use a mux, a multiplexer, wherein you have this code. You take this wind model and then you feed that to the wind, and let's see if it works. And then you should be able to see your wind. As you can see, this is the gust property of the wind that is coming from the Dryden model. So what this is telling me is the values of the wind velocities, the gust wind velocities for altitude of 300 meters and the airspeed of 20 meters per second is something like this. Now this wind velocity, the gust, is added to the steady state velocity, and the steady state velocity is fed to this wind input, and then you will have a totally different result. Yeah, mux needs to do the top element first, because the top elements, these elements are the constant values of the velocity, and these values are the gust values of the velocity. Dryden model will give you the gust values. Okay, so with this, you should be able to run your force moments, but the big question still remains. And the big question is, how do we take all these codes and put it in one single code? And actually, it's quite simple. Okay, what is the matrix, the bottom identity? And I will show you how that matrix looks like. Tyler, you got your answer? Do you see the matrix? Okay. So before I go to the last part, I just want to make sure that your code is working. Were you able to get the code working? Okay, if you have copied the code from the chat, but if it is not working, in the latest announcement, I have added all the Simulink files that we created in this lesson. So you are just welcome to download the zip file from the latest announcement. The same zip file is in the MATLAB codes, and we will have all these working codes for you. I just uploaded those before the class. Okay, now the last part, and it will take only 3 minutes to finish, so bear with me. The last part is, how do we do all this derivative 1 in the Simulink? And for derivatives 1, again, same process. We go to derivatives 1. Now let's go back to the changes that we made to derivatives 1. What you need to, if you are downloading the new MATLAB, I recommend you take all your old work and make a copy and save it in the Dropbox or some other folder, and then download MATLAB. Because if your all previous work is inside the default MATLAB directory, if you uninstall the original MATLAB, it will ask you if you want to get rid of .m files. So if you don't want to risk that, I would recommend you save all the files in a separate folder. Okay, so next question is, how do we modify derivatives 1? Now here, there is the same problem. Can you see that here there is out 1? That is not going to work. So what I'm going to do is, I'm going to go back and I am going to make some changes. The first change that I'm going to make is I'm going to use this function, copy. So let's start from the beginning. I will go to Simulink. Go to Simulink, create a blank model. In the blank model, go to library browser, go to user-defined function, MATLAB function, double-click MATLAB function, delete all this. Go to derivatives 1 and copy derivatives 1, copy, paste it inside the MATLAB function, the latest MATLAB function that we created. Now here, this data structure will not work for Simulink. Out1 will not work for Simulink. So I need to make the changes. And that's why we made the changes in the previous MATLAB function. All these forces, copy, paste, and this is going to be force underscore 1, force underscore 2, force underscore 3, torque underscore 1, torque underscore 2, torque underscore 3, and then if you go down, you have fx, fy, l, and n, and then finally nothing else is changed. So you will save this. And I'm going to say derivatives run. One. Yes, John, I will give you the file, but one thing I want to tell you, all these files are in the latest announcements. So first 35 lines. Yes, Randy, I will upload the class recording. And now when you go to your MATLAB file, you will have tons of different stuff. You will have t, states, derivatives, x dot, and so on. Now what we need to do is add an integrator. Add initial conditions to the integrator. I'm going to call all my initial conditions 0. So there are 12 initial conditions. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Add initial conditions, then add scope. Then you need a clock. Then the states need to come from the initial condition, the solution. And the F states, I'm going to add a constant. Which is 0, 0, 0, 0, 0, 0. So I'm saying all the forces, initial forces are 0. Click OK. Assuming things are okay, run. And again, it will give you an error because of the data structure mismatch. So we go back and then fix the data structure mismatch, which is over here, which is force moment SP3. And this data structure mismatch is same as the previous. So what I'm going to do is I will go to the MATLAB function, file, save as. I will say force underscore moments SP4, force moments SP4. I'll change this to force moment SP4. Save. Go back where the issue is having, change this to 4. So this force underscore moment SP, let me see, force underscore moment SP4. And then you should be able to run the code. So once again, copy all this. Paste. Save as. derivatives, you got force moments, and then run this code, and then you will still see there are some errors, and that needs to be changed. You have to change the data structure. And just to give you an idea, is all these files are uploaded in the folder. So if you go to Canvas, all these files that you need are inside the robotics 2 modules. And I'll show you just this thing. So go to robotics system 2, go to announcements. The latest announcement has all the files that are working. So you can download this project 3 class discussion simulink.rar. It will contain how to do all the files in here are working. My apologies for going 15 minutes out, but I will stop here